Next up, Ben Dean is going to be telling us about message handling with Boolean implication. And I'll hand that over right now.
My name is Ben Dean. I'm a principal engineer at Intel, where I work on power management inside the CPU package. I work on a team with Michael Case and Luke Valenti, and we're using C++20 to bring abstractions to that highly constrained embedded environment. This talk reflects a small part of that. Before we start, some quick disclaimers. All the code you're going to see is simplified for slides, but it is real code that exists in Intel's compile time initialization and build library, and you can find it on GitHub. This talk is shortened for pure virtual C++, so let's get into it. This talk is about a message handling library. Now, message handling is a common problem in many codebases. Maybe many of you have codebases that do message handling. You get some data off the wire or from some other external source, and you need to decide what it is and how to deal with it. And that usually means looking at some of the fields inside the message and dispatching accordingly. So we'll talk about how this library does that in a compositional way that minimizes the work needed at runtime. First, we'll see how fields and messages are defined in this library. Then the idea of a matcher that identifies messages so we can dispatch them. And then, for the bulk of the talk, we'll dive into how matches are composed together and how they're simplified. To begin with, I need to give you a bit of background to make sense of what's to come. So let's look at some nouns of the library, messages and fields that make them up. We can define a field by giving it a name and a type. That type is its API type, if you will, the type the field presents to the outside world. For our purposes, it's almost always a fundamental type and trivially copyable. And then we need to specify where the field lives in the data layout. Conventionally, we do this with the word index in the message and the span of bits within that word. Notice here that the bit range includes both the least significant bit and the most significant bit. At this layout level, we're dealing with data in bits, and it's common for fields to be just one or a few bits. Here's perhaps a familiar example of a message. This is the IPv4 header, as seen on Wikipedia. It has some fields here, version, internet header length, and so on. Let's see how a few of them look in code. This is what definitions for those fields look like in C++. Each has a name and a type, and then a locator for where it lives in the data layout. Version is the first 4 bits, IHL the next 4, etc., etc. A field knows how to read and write a value of its type into the data layout. We call those functions extract and insert, and this is what they look like. The range here is any range, like an array of bytes, for instance. Notice here that a field is just a definition. It's an empty type. There's no value in a field. The value is in the data, and the field knows how to deal with it in a type-safe way. So now a message definition is just a collection of fields. It's also an empty type. To make an instance of a message, we put together the definition with the data. This is what it looks like in C++. The message is effectively the type list of fields. Owning here is a type alias that provides a right-sized array and get and set methods so we can use them to read and write field values. And there's some UDL machinery here to make the interface a bit nicer. But that's all there is to field and messages. Machinery in the type system that allows us to make these things in a declarative way and work safely on the plain data underneath. Okay, so now we know what fields and messages are, let's look at how to identify messages that come off the wire using what the library calls matchers. What's a matcher? It's a predicate on a message, a function object that, given a message, returns a Boolean value. Here's what a concept for a matcher T might look like. Now, I'm cheating a bit for the slide. Assume we have a prototypical message here. So when we call the matcher on that message, it gives us back a Boolean value or something convertible to a Boolean. You get the idea. Here's a concrete example. If we want to dispatch based on a certain field being a certain value, here's a matcher that does that. So when we call its function call operator with the message, it's going to extract the right field and test to see whether it's the right value. Okay, it's quite straightforward. We can make that equal to matcher a bit more generic by templating over the relational operation. Instead of just equality now, we can pass in the operation we need. And the standard gives us function objects for less, greater, etc. So we can use those. Now we have matchers that can test equality or whether a field is less than a certain value, etc. And we can use template aliases to make it as easy to use as the concrete equal to version we saw on the last slide. Now, a matcher is a predicate. It's a function that returns a bool, so we can compose matchers just like we compose bools. if we make class templates for and, or, and not that wrap the underlying matches and implement the function call operator, we'll be able to compose matches in an expression template. Here's what that looks like in C++. When we AND together two matches, we wrap them in an AND T. And the function call operator here does the obvious thing. It calls the two wrapped matches, ANDing together the results. I bet you can guess what OR looks like. It looks just the same as AND, except with OR. And NOT is even simpler because it only wraps one matcher. Notice that AND T, OR T, and NOT T here are still matches. They all implement the function call operator, taking a message and returning a bool. So now with AND, OR, and NOT operator overloads that work on matches and return the appropriate wrappers, we have a simple expression template thing going on. Now we can combine matches with the usual Boolean operations. Let's pause for a second and see what we've defined so far and what it looks like in code. We've got ways to define fields and messages. We can declare a callback. That's the combination of a matcher and a function. When we get some data off the wire, if the matcher matches that data, we're going to call the function. That's what handling a message means. And a handler wraps up the callbacks so we can call a handle function with the raw data. You can see here how we define a matcher in user code. That type field equals 42 is a little DSL that ends up being an equal to matcher that we saw before. And then the function takes a const view of that message. That's another message instance type, like the owning type that we saw before, except this time it's just a view type. But it has all the same type-safe machinery for reading fields. Here's another example of that matcher DSL. The AND and OR operators here are what we saw before, and the relational operators are overloaded to produce the relational matches we saw before. So this ends up being a convenient way to express matches. Bear in mind the expression you see here becomes an expression template. It's an empty type that expresses the constraints on fields in a message. All of the literals you see here are compile time values that get put into the type of the matcher. And the resulting matcher itself is a template expression tree. Now, we've made it easy for users to express arbitrary matches, and we'd like to make sure that doesn't translate into unnecessary work at runtime. All of these matches are empty objects whose semantics are in their type, so we'd like to take advantage of that at compile time and do the least work at runtime. At this point, I had to think for a while. These are the kind of expressions I thought about. How is the library to know how to simplify things like this? We can look at these expressions as humans and understand, for example, that less than 5 or greater equal 5 will always be true. Less than 5 and less than 7 requires us only to check that the field is less than 5, because if it's less than 5, then it's also less than 7. And the last thing here is saying that the same thing on each side of the AND. Not less than 5 is the same thing as greater or equal 5. So now we come to the real problem of how to simplify things at compile time. Well, how was I going to do that? Of course, I knew the rules of how to simplify regular Boolean algebra, but it wasn't obvious to me how to express this to the library in a generic way, so I had to think. Well, I took a step back and I figured a good place to start was with the basics. We're doing Boolean algebra, so true and false are the atoms, and here they are in matcher world. They're called always and never. Always is the matcher that returns true, whatever you give it, and never is the matcher that always returns false. And you can see these are both matchers. They're function objects that take messages and return booleans. It's just that we don't mind what kind of message it is. Okay, so that was easy. So we have an expression template. If we know, for example, that some matcher inside there is always going to turn out true, we could transform the tree and replace it with an always. And that might mean that we can simplify further. Here's an example. Here you can see the tree representing A and not B or C. Now A, B, and C could themselves be arbitrary matches, including and OR terms. Now, if we know that C is true, then we know that not B or C is true, because you've got a true in an OR term. So the whole OR term becomes true. And if we know that, then we know that the AND matcher at the top would collapse to just A, because it'd be A and true. I should say at this point that this matcher library is designed to work with another library that computes indices on the fields and uses that ahead of the matching to partially dispatch. So it is possible by the time we get to evaluating a matcher that we will know it will be true because it involves a field we already indexed on. And we'll know this at compile time. Well, the next thing is to write a simplify function, and then we can overload it for the and, or, and not matches. The default simplify function does nothing at all to simplify, it just returns the matcher it's given if we don't know any better. What does simplify look like for and? Well, we know what to do if either side is always or never. First, we'll recursively simplify each side of the and. Then if either side is never, we know that the and itself will be never. If either side is always, the result of the and will be the other side. Otherwise, well, we simplified both sides and we can't do any better than that, so we and them together. And we can write a very similar looking function for or. And we can go to Wikipedia and find all the rules of Boolean algebra and code them up. There are quite a lot. Here are some of them. There are even more, considering that we have to deal with each expression being both ways round. For example, a and true simplifies to a, and true and a also simplifies to a. This gets verbose pretty quickly, and it's quite limited in what it can simplify. How do we simplify less than 5 or greater equal 5? We know this should simplify to always, but these matches are different types. How does the library simplify this? If we could know that these matches are complements of each other, we could simplify the expression. Maybe we can do that by customizing the application of not. So I introduced a customization point, negate. Instead of just wrapping a not around the matcher, I call a negate function which can be customized, and here's our new operator overload for not on a matcher. Now instead of just returning a not t, we're calling this negate function, which we can overload. Well, the default thing to do is still to wrap a not around the negated matcher. That's what we were doing before, that's easy enough. But now there's another overload that springs to mind. Negating a not matcher can just return the original matcher inside, instead of double wrapping it with not, so that's nice. Now I think I can write an overload for a relational matcher. What I need to do is return a new matcher whose operation is the inverse relational operation. And I can code up a simple function with a half a dozen if const extra branches inside it to deal with inverting each of the half dozen relational function objects. Now the library has a generic idea of negation, which means it understands those relationships between the relational matches, and it can simplify things like this expression by normal Boolean algebra methods. Have you noticed that so far all the functions we've written have been just a few lines, or at most 1 or 2 lines in each of a few if const extra branches? This is a good sign that we're going down the right compositional path. Okay, this next problem on my list of problems that I was thinking about was a bit harder. So again, we know as humans that less than 5 and less than 7 is really the same thing as just less than 5, because if a field is less than 5, it's necessarily also less than 7. And there should be no need to evaluate the second matcher here. So I thought about this and I had an idea that took me about a week to incubate. And here's where we have a quiz. A quiz in a recorded talk. Yeah, the questions are easy, I hope. Ah, you say, but are the answers easy? Yes. Okay, first question. If I have a thing of type A, and I have a function from A's to B's, can I make a B? By the way, some folks aren't familiar with this syntax for a function pointer type. This is just a function pointer type using trailing return syntax. So given this, can I make a B? And the answer is yes, of course. It's not a trick question. I can just call the function with the A. Next question, and it's really the same question, slightly different. If I have an A and a function from A's to B's, this time, can I make a pair of A and B? And the answer is yes again. A is copyable. I'm not bothered about non-copyable types here. Those are C++ isms. We can call the function with the A to get the B, and then we have a pair of A and B. And now the last question in this short quiz. This time I have a variant of A and B, and the same function from A's to B's. Can I make a B now? And the answer is still yes. If the variant already contains a B, I'm done. But if it contains an A, I use the function again to make the B. Okay, hopefully that was quite an easy quiz, but what was the point of it? Well, believe it or not, you just did Boolean algebra, even if it didn't seem like it. Here's the function from A to B. Now, what does that function arrow mean? It means implies. It's the same thing as Boolean implication. Let's reinterpret the quiz. When we say, I have an A, we're saying A is true. And when we say, I have a function from A to B, we're saying A implies B is true. And when we say, can I make a B, we're asking, is B true? When we say, can I make a pair of A and B, we're saying, is A and B true? And when we say, I have a variant of A and B, we're saying A or B is true. In each of these cases, the type interpretation maps directly to a Boolean algebra interpretation, and we call this the Curry-Howard correspondence. This is what reasoning with types means, and the good news is that you already knew the answers to those questions. You just might not have recognized that they were Boolean algebra questions. So you already have an intuition for implication. Let's take a closer look at it. The idea I had was that I could use implication to simplify. So what is implication? It's just another binary Boolean operation. We're all pretty familiar with and or. Implies is just a different truth table. And here they all are. The third column is A and B, the fourth column is A or B, and the last column is A implies B. Now, thinking about implication can be confusing for some reason. I think because we tend to say things like, if A then B, which obscures the idea that A implies B is a proposition. It might be true or false. So it's sometimes easier to think just of implication as a plain old Boolean operator. There are a couple of implication propositions we can take note of, though. Here is the first one, the easy one. Anything implies true is a true proposition. And we can see this from the non-grayed outlines of the truth table. False implies true is true, and true implies true is true. The second proposition is harder to intuit, but it's clear from the truth table. False implies anything is a true proposition. False implies false is true, and false implies true is also true. False implies anything is hard to grok, so here are a few explanations that might help. I can say all unicorns have pink polka dots. This is a true statement. Unicorns don't exist. The set of extant unicorns is the empty set, so any statement I make about unicorns is true. Please disregard the fact that unicorns you see in movies are white. Here's another example of implication. It's raining implies the ground is wet. What would make this statement false? Only if it's raining and the ground is not wet. If it's not raining, the ground might still be wet, or it might not be, and the statement is still true either way. Another way to think about this is in terms of sets. It's raining implies the ground is wet is another way to say the set of times when it's raining is a subset of the set of times when the ground is wet. Okay, so how does this tie into simplification? Well, I wrote out the truth tables for and, or, and implies next to each other. And here's what I realized. If A implies B is true, then A and B is the same as A, as you see here in columns 1 and 3. And A or B is the same as B, as you can see in columns 2 and 4. So I realized I could use implication to simplify expressions. So let's look at how that can work. Here's one of my original problems. Why does this simplify to just less than 5? Because if x is less than 5, it is less than 7. In other words, less than 5 implies less than 7 is a true proposition. And if we can express that to the library, it will be able to simplify. Okay, I thought, let's make a customization point for implies. The default is that a matcher implies itself. It doesn't imply a matcher of a different type. And once more, this is just a one-liner. This code is saying that x implies x is a true proposition. Well, we also have true and false. We call them always and never. So we can code up the facts about implication that we saw just now. And here's the C++. This is saying any matcher implies always is true. And in the second case, never implies any matcher is also true. Now, if you're really paying attention, you might notice that these two overloads produce an ambiguity if we try to compute never implies always, because in that case, both of these overloads will match with equal precedence. But we can solve that problem easily enough with an overload that deals specifically with that case. So just one for never implies always. We can also warrant implication involving or terms. This is saying a matcher M implies A or B if and only if M implies A or M implies B. And we can warrant implication involving AND terms. A and B implies M if and only if A implies M or B implies M. Both of these functions are fairly easy to prove with a half dozen lines each of Boolean algebra, but that slide didn't make the cut for this version of the talk. We can also implement implication between our relational matches. This is the form of our less than 5 and less than 7 problem. Less than 5 implies less than 7 is the same proposition as 5 less than 7. Strictly, it's 5 less than or equal to 7, but we already took care of the case that a matcher implies itself. So this is the implementation of implies for relational matches. It uses the relational operator on the values, another one-liner. In fact, we can go further than implication between matches with the same relational operators, because we know about relationships between less than and less than or equal to, for example. So we can add a few functions for the short list of those kinds of combinations. This is what simplified looked like for an AND term earlier. Now it looks like this. We've genericized it in terms of the implies and negate customization points. If either side implies the other, the AND term collapses to the appropriate side. If either side implies the negation of the other, the AND term must be false, or never. Otherwise, the sides have no relationship that we know about, and it just remains as an AND term. And you can imagine a similar overload for OR terms. It turns out that this does the trick. Using implication in this way gives us a huge helping of Boolean algebra simplifications. We wrote maybe a dozen functions, some containing a few if-const expert cases. I think no case was more than a one-liner. And what we got was a generic ability to simplify any matcher expression, and the ability to define matchers outside the library, provide a couple of overloads for them, and treat them the same. And all of this simplification happens at compile time. At this point, I had a couple of observations. One was that I might once have thought of A implies B as merely not A or B. They have the same truth tables. But I was really using implication as a building block here. I think it wouldn't really have been possible to do the same manipulations if I didn't use implication this way. I'm not evaluating the terms, I'm warranting the truth of the implication proposition. A few days after getting to this point, I realized something else. We're manipulating matchers. Matchers are predicates. So implies is a higher order function. And because the matcher semantics are encoded in their types, we're able to actually evaluate implies without evaluating the matchers, which is a rarity in my experience. Most higher order functions eventually evaluate the functions they're given. So after doing this, I continued with my life. And then a few weeks later, I had another realization. I realized that implication defines a partial ordering on matches. Can functions in general be ordered? No, but matches are predicates. A given matcher matches some things and not others. Matcher A might match fewer things than matcher B, and that can give us a partial order based on how many things are matched. If everything that B matches is also matched by A, then B implies A. And under an ordering interpretation, this also means that B is less than or equal to A. And this gives us another way to interpret that tricky false implies anything. False is never the matcher that matches nothing, or the empty set. And of course, the empty set is a subset of any set, so it's less than everything. And this is another way to say that false implies anything. And this is what the C++ looks like for ordering matches. This is the spaceship operator. If neither matcher implies the other, they're unordered. We can't do anything with them. But otherwise, they can be ordered according to which way around the implications are. This is where my talk must end. There is a lot more here, but that's another talk. Actually, more than one other talk. As I said earlier, this library, the matches library, fits in with another library that computes indices on fields at compile time, so that runtime dispatch can be very cheap and easy. But we don't want to tie together the knowledge of which fields are indexed with the matcher code. The goal here is to be able to express matchers easily, and then use field indices to speed up selected use cases. And the details of how we do that are in the longer version of this talk and in Luke Valenti's companion talk. And we do a lot more with Boolean algebra to make the indexing library and the matching library mesh together nicely at compile time without having to overly constrain our expressions because of performance concerns. It only remains for me to thank you all and leave you with my conclusions. Like many of us, I learned Boolean algebra as a teenager, and I didn't really give it much thought after that. I thought it was too trivial to bother with much when I was trying to apply myself to complex problems. But it really does underlie everything we do. And implication is a very important operation that is typically given even less mindshare. But every time we write a function, we are expressing an implication. And when we really understand and apply Boolean algebra, it can do some surprising and powerful things. Thank you very much for listening.